The topic of this set of lectures is going to be a bit more involved than the previous ones. And in fact, Weinberg advises, and I quote, "This section lies somewhat out of the book's main line of development and may be omitted in a first reading." Unquote. However, the mathematics involved here, though a bit non-trivial, is actually rather fascinating. So I would like to discuss the issue of projective representations, their existence or inexistence, as the case may be, and that is going to occupy us for a few sections. Now let me remind you that when you have a symmetry operation capital T, there is a corresponding unitary operator U of T which acts on the Hilbert space. And since the physical things, the states, are in one-to-one correspondence with rays and not vectors, the issue of these operators, which could be either unitary or anti-unitary as Wigner had shown, is slightly more complicated than in the corresponding classical case. In particular, if you carry out two successive symmetry operations, T bar first and then T, you are actually applying the unitary operators UT bar and then UT, of course, that's the product UT bar, on a given Hilbert space vector. Symmetry demands that the corresponding product transformation TT bar will have a corresponding unitary operator U of TT bar, and symmetry demands that U of T bar acting on a vector will definitely lead to a vector which is in the same ray as U TT bar acting on the same vector, but the result need not necessarily be exactly the same vector. In other words, there could be an extra phase factor involved. We had also argued in a previous lecture that this phase factor has to be independent of the particular state that the product operator is acting upon. So what you would have is this relationship that you can see on your screen right now. UT times UT bar would be e to the I phi, which is a function of T and T bar, times U TT bar. This phi, of course, has to be a real number because this overall factor has to be pure phase. This, of course, differs from standard representation in group theory. A representation would map every symmetry operation to a corresponding operator such that UT bar would be equal to UTT bar. The presence of this extra phase in the I phi T comma T bar is what leads these things to be called projective representations, or more colloquially, representations up to a phase. The question that is going to occupy us in this set of lectures is, given a particular Lie group, or rather its corresponding Lie algebra of the generators, is it essential to have a projective representation, or is it possible that all projective representations of such a group are actually trivial? In order to understand what this trivial projective representation means, let us start with a situation where you have a non-projective representation to begin with. Let U tilde T correspond to a non-projective representation, that is U tilde T times U tilde T bar is actually equal to U tilde TT bar without any phase factor. Now, given the fact that the unitary operators map vectors to vectors, whereas physically we are more interested in rays to rays, what you can always do is redefine the operator involved by introducing an extra phase. So instead of U tilde T, you could use UT, where U tilde T is related to UT through an extra phase. U tilde T is UT e to the power I alpha, which may of course depend on T. Now, if we substitute this in the non-projective representation formula, U tilde T bar, U tilde T bar, what we get is UT e to the I alpha T, that's of course U tilde T, times UT bar e to the I alpha T bar, utility bar that is, must be equal to u tilde tt bar, and that's u tt bar to the I alpha tt bar. Of course, this implies that the UTs furnish a projective representation. UT bar is not equal to UTT bar, but there's an extra phase factor phi of t comma t bar, given by alpha tt bar minus alpha t bar. Now, given a situation like this, that is, given a phase which depends on both the symmetry operations, for which there exists a function alpha of a single input t, which satisfies phi of t comma t bar equals alpha tt bar minus alpha t bar, it's easy to see that you can always reverse the process that we carried out a while ago and go back to u tilde t, that is, go back to a situation where there is no phase. So you can remove the phase trivially by redefining the operators. Although you do have a projective representation in such cases, and which implies that all Lie algebras definitely have projective representations, these are trivial cases and we are not really going to consider them as genuine projective representations or intrinsic projective representations. Now, irrespective of whether you can get rid of this phase factor phi by redefining the phases of the individual operators or not, there is one important restriction which all these phase factors must obey. And in order to understand that, we have to fall back on the fact that u of t's, after all, are operators, and as a result, they obey the associative property. U of t3 times u of t2, u of t1 must be u of t3, u of t2 times u of t1. And using that, what we get is the following. On the left hand side, u of t2, u of t1 becomes e to the I phi t2, t1, u of t2, t1. On the right hand side, this bracket ut3, ut2 becomes e to the I phi t3, t2 times u t3, t2. Of course, you have u of t3 on the left here and u of t1 on the right here. Now, since we are assuming that the operators involved are unitary, the e to the I phi t2, t1 can move right across, and now you have the product ut3, ut2, t1 on the left. On the right, you have ut3, t2 times ut1 apart from the phase factor. Now this composition ut3, ut2, t1 leads to u t3, t2, t1. I am writing this without a bracket because we know that symmetry group operations are associative. So it doesn't matter whether I put in a bracket or not. But this actually gives rise to an extra factor of e to the I phi t3, t2, t1. On the right hand side, we also get an additional phase factor, but this time the phase factor is e to the I phi t3, t2, t1. And of course, apart from that, the unitary operator involved is the same on both sides. Now, since these two sides have to be equal, and that's essentially what associativity tells us, we must have this restriction on the phase factor phi. Phi of t2, t1 plus phi of t3, t2, t1 must be the same as phi of t3, t2 plus phi t3, t2, t1. This is nothing but a reflection of the associativity of the operators. Now, our trivial phase factor phi of t bar given by alpha t bar minus alpha t bar definitely satisfies this. Let's just check whether that's true. The check is rather simple. The LHS in this case will be alpha t2, t1 minus alpha t2 minus alpha t1, that's for phi of t2, t1, plus phi of t3, t2, t1, which is alpha t3, t2, t1, the product of all three operators, minus alpha t3 minus alpha t2, t1. Now, cancelling out the alpha t2, t1, we'll end up with this expression on the left hand side. Alpha of t3, t2, t1 minus alpha t1 minus alpha t2 minus alpha t3. This rather obvious symmetry between t1, t2, t3 in the expression here shows that the right hand side must come out to be the same thing. And you can of course verify that by a direct calculation. I just did not bother to calculate the whole thing here. It's sort of obvious from the expression itself. Going back to the question of whether we can get rid of this phase factor in a projective representation or not, let me put it this way. If there exists a function alpha of t such that the phase factor phi t2, t1 differs from 0 by alpha t2 t1 minus alpha t2 minus alpha t1, then the phase factor essentially is the same as 0. Now this essentially as the same is a notion that we capture by means of an equivalence relation, and the corresponding equivalence class is what we call a Tuco cycle. Now there's a bit of nomenclature related problem here. Many authors actually call the phase factor e to the I phi t2, t1 a Tuco cycle, and some authors call equivalence classes of these phase factors, which effectively can be interchanged by just redefining the phase of the individual operators involved, as a Tuco cycle. We are going to use the latter nomenclature. To be more formal, phi tilde t2, t1 is said to belong to the same Tuco cycle as phi t2, t1 if there exists a function alpha of t such that phi tilde t1, t2 minus phi t1, t2 is alpha t1, t2 minus alpha t1 minus alpha t2. Now, in the same Tuco cycle is an equivalence relation. That's something which is very easy to check. Of course, you have to check reflexivity, symmetry, and transitivity. Reflexivity is sort of trivial. Phi t1, t2 is obviously in the same Tuco cycle as phi t1, t2. Even the name sort of implies that. But in this case, the difference on the left side would be obviously 0. And on the right hand side, all you have to do is use the function alpha of t equals 0 to get there. Now, if phi tilde is in the same equivalence class as phi of course has to be in the same equivalence class as phi tilde. But that's sort of obvious even from the equation itself. All that happens when you interchange phi and phi tilde is that left hand side changes sign. And all you have to do is replace alpha by minus alpha to get there. Transitivity takes very little extra work to prove. And once you've proven all this, it's easy to see that in the same Tuco cycle is really nothing but an equivalence relation. And this Tuco cycle is really the equivalence class corresponding to it. It's a set of all functions related to each other in this particular manner. Now, it's very easy to show that if you have two phase factors phi tilde and phi which belong to the same Tuco cycle, then you can actually go to a representation which has phi as a phase factor from a representation which used to have phi tilde by just redefining the phases of the individual operators. And we have seen a special case of that for the trivial Tuco cycle. The trivial Tuco cycle is simply the set of all functions phi t, t bar such that there exists a function alpha such that phi t, t bar is alpha t, t bar minus alpha t minus alpha t bar. And these are of course all functions which are Tuco cyclic with 0. And if the phase factor of a projective representation belongs to the trivial Tuco cycle, then it can be converted to a standard, that is a non-projective representation. This is essentially what we have said earlier, but in a sort of converse way. The real question that will occupy us here is, does a symmetry group allow non-trivial Tuco cycles? In other words, does it have intrinsically projective representations for which the phase factor cannot be gotten rid of by just redefining the individual phases? As you will see, the answer to this question happens to be quite an involved one. But before we go there, we need to clarify a few more basic features first. And this has to do with the Lie algebra that arises out of a Lie group. Remember that we had earlier already discussed this issue. In a Lie group, a given element T is actually parameterized by a bunch of parameters, R distinct real parameters for an R-dimensional Lie group. Let's call them theta 1, theta 2 up to theta R, and collectively we will call them theta vector. Now we have this convention that a value of 0 for each and every one of the parameters will represent the identity. And we are considering a situation where we are close to the identity, that is, the parameter values are close to 0. Now, we have already seen that because a 0 value for the parameters correspond to the identity, and because we are talking about a situation that is continuous, for small values for the parameter, T of theta will be close to the identity operation, and the corresponding unitary operator U of T of theta will also be close to the identity. In particular, we can expand this in powers of the components theta. And this gives rise to the notion of generators. And we had already seen before that the basic structure of the Lie group, in particular the group composition rule, ensures that the generators of this Lie group, the first order terms in the Taylor series expansion for U of T of theta, obey a commutation relation. In other words, the commutator of these generators is again a combination of the generators. But in order to establish this, we had to use the fact that U of T of theta furnished a representation, a genuine non-projective representation of the Lie group. The question that we have now is exactly how does the presence of this phase factor affect the corresponding Lie algebra, the commutation rules between the generators. Let me remind you that, as we said just now, U of T of theta can be expanded in a power series of the parameters. It starts with the identity, because of course when the parameters are 0, you are going to get the identity. Then you have a linear term written I Ta theta A, where TAs are the so-called generators of the corresponding Lie algebra. The second order term is something which we have written as half TBC, theta B, theta C. TBC of course has to be symmetric and B and C. And as we had already seen before, and we will see again, this operator TBC is directly connected to the generators T1, T2, T3 and so on through the group composition rule. Indeed, though we are not going to prove this, all the higher order terms will also be directly related to the generators themselves. Now the new thing that we have in a projective representation is this extra phase factor phi of T of theta bar. And we need to take a look at exactly what the structure of this phase factor phi is when expressed in terms of these parameters. Now in order to see that, let me remind you that because T of 0 corresponds to the identity and U of T0 of course is the identity operator, we must have U of T of theta times U of T of 0 and these two operators in the other order multiplying themselves, giving you U of T of theta. And in other words, the phase factor phi must vanish when one of the two operators involved happens to be the identity. So phi of T of theta T of 0 is going to be 0. So is phi of T of 0 T of theta. And this immediately tells us that if we expand the function phi, which now depends on theta and theta bar, note that although I am putting an arrow on top of theta and theta bar to denote that they are not a single parameter, possibly they are a collection of r different parameters, we are simply going to call them theta and theta bar and not vector theta bar. Anyway, because of this demand that when one bunch of parameters vanish, phi must be 0, the form of phi of t of theta, phi of t of theta bar, when we expand this out in powers of theta and theta bar, must be the following. The lowest non-trivial term must be quadratic and mixed. That is, it must be of the form FAB, theta A, theta bar B, where FAB are just some real numbers. Of course, you can have higher order terms, and usually you will, but we will see that this particular term, FAB, theta A, theta bar B, is of the biggest importance as far as we are concerned. On top of this, let me remind you that since we are dealing with a Lie group, we are dealing with symmetry operations which are parameterized by a bunch of vectors, of course. But when you compose two such symmetry operations like t parameterized by theta with t parameterized by theta bar, the resulting symmetry operation will be parameterized by f of theta and theta bar, where f is a vector valued smooth function. Vector valued means simply R component for us. In addition, if you were to replace one of the parameters by the null vector, that is, replace all the components of the vector by 0, then we are actually talking about the identity. And this immediately tells us that FA, the ith component, theta vector, 0 vector, is the same as FA of 0 vector, theta vector. And this must be the ith component of theta. Now this has already led us earlier to the following conclusion. If we were to expand out the function FA in powers of theta and theta bar components, the lowest order term must be theta A plus theta bar A, and these would be the only pure theta or pure theta bar terms in the expansion. The quadratic term in particular must be FABC, theta B, theta bar C. And of course, you can have higher order terms, but all these higher order terms must be mixed. You can't have terms like theta A, theta B, theta C. As we had already seen before, these constants F, A, B, C are actually related directly to the so-called structure constants of the corresponding Lie algebra. All we are going to take a look at now is how the presence of these extra phase factors phi is going to modify the commutation relations in which the structure constants play an important role. So for this, all we have to do is write down the projective representation formula using the expansions for UT, UT bar and UTT bar as we described a while ago. And what you have, of course, on the left, this is U of t of theta written up to quadratic powers of theta. This here is U of t of theta bar written again up to quadratic powers. This is e to the I phi t of theta bar written up to quadratic power. And here what we have done is we have written U of t of f of theta bar. What we have done is we have expanded out the f of theta bar up to quadratic power here. Here, of course, we have ignored the quadratic terms because since we are working only up to quadratic terms, the product of these two would be enough to give us quadratic terms. You don't need any more. There are, of course, other additional terms beyond this. Now, all we have to do next is just expand this thing out and compare terms order by order on both sides. The left hand side expands out rather simply. You get identity times identity giving you this. ITA theta A times identity and identity times ITA theta bar A gives you this linear term. Then you have to be careful about gathering the quadratic terms together. One quadratic term you immediately get is this thing times this identity, which is this one. The other quadratic term you have on the left hand side is the product of these two. And here the only care that you have to really exercise is that you have to be careful about the dummy index. You don't want to use the same dummy index A for both of these. In fact, for later convenience, what we have done is use B and C respectively. So this can also be written down as ITB theta B and this is ITC theta bar C. We have just multiplied them together and I've got I square, that's minus 1, times TBTC theta B theta bar C. So that's the left hand side up to quadratic order. Now, if you have actually listened to my earlier lecture on how the Lie algebra and structure constants arise in the same series, this should all be familiar stuff to you. The right hand side takes a bit more care, but that's also pretty straightforward. The linear term, identity times identity, that's of course the zeroth order term. The linear term is here, this thing times identity. Now the quadratic terms take a bit more effort. One is obvious, this times identity. Then you have this particular term which is also a quadratic. And then you have quadratic terms which you get by multiplying this out. So theta B, theta C, theta bar B, theta bar C, theta B, theta C bar plus theta bar B, theta C. The four terms which you get by multiplying this out. So this is essentially the projective representation formula written up to quadratic terms in theta and theta bar. Now, of course, the identity matches on both sides. You can cancel that out. The linear term also cancels out. These terms cancel out. And one more thing happens. These two terms look different, but you can of course switch the dummy index. So write this half TBC theta bar B theta C also as half TCB theta bar C theta B. And because TCB and TBC were taken to be equal by definition at the very beginning, the two terms here are actually one and the same. So they really give you TBC theta B theta bar C. So you notice that only terms that are left here, all of them have theta B theta bar C except this one. But that's also easily remedied. All I have to do is just change the dummy indices to FBC theta B theta bar C. And now we can immediately read off the relationship, which is TBC, coming from the two half TBCs, plus TBTC, which is just this brought to the other side, is equal to minus IFBC minus IFABC times TA. In fact, this term is exactly what we had earlier. Because of the projective nature of the representation, you now have an additional term, which is essentially minus IFBC times the identity operator. Now, what we did earlier with the non-projective representations, we can repeat once again here. Notice that we do know that TBC and TCB are equal. This equation that we have written down tells us that once we interchange B and C, we get TCB plus TCTB is minus IFACBTA minus IFCB, and subtracting the two immediately gives us this very, very important result. The TBC and TCB cancel out and you have the commutator of TB and TC, and it works out to be something times TA, actually a sum over TA times some constants which depend on A, B and C, ICABCTA, where CABC is FACB minus FABC. Now this should be the familiar structure constant from the Lie algebra that we had met before. But in addition to that, you have one more additional piece. You get I times CBC times identity, where CBC is simply FCB minus FBC. So the presence of this extra phase factor in a projective representation has this consequence on the commutation relations. Instead of the commutator of TB and TC being a linear combination just of the generators themselves, there are terms which depend also on the identity operator, or you can just say that you have extended your original set of generators with the identity, which of course commutes with all of the generators themselves. So what we have, are what are called central charges. So projective representations essentially give rise to what are called central charges, additional terms in the commutators, which in turn commute with every one of the generators. Now, the structure constants CA, BC are things which are already familiar to us. We now have these new constants CBC to worry about. And just like the structure constants, these new ones also have a restriction on them, which follows from the so-called Jacobi Identity. Remember, the Jacobi Identity is simply the statement that if you take the commutator of x and y with z, that is, the commutator of x and y commutator with z, and then cyclically permuted the elements around, the sum of all three would be 0. Now that's very easy to prove starting from the definition of the commutator. Now let us start by taking a look at the commutator of this kind between three generators. TB, TC's commutator of that with TD. Now of course, according to our new rule, TB-TC's commutator is ICABC-TA plus ICBC times the identity, and we have to calculate the commutator of that with TD. Since the identity, the so-called central charge, commutes with every generator, it drops out of the commutation relation, and you are left with I times CABC times the commutator of TA with TD. But now the commutator of TA with TD gives rise to an additional I, which gives rise to the I square factor outside, times CEADTE plus CAD times the identity. And when you gather them together, the following conclusion arises out of the Jacobi Identity. Remember, the Jacobi Identity tells you that if you took this expression and cyclically permuted B, C and D, you would end up with a sum of 0. And that gives rise to the result, the CABCCEAD. Of course, the sum over A here is very much implied by the summation convention. But E, B, C and D are free indices. If you take this expression and cyclically permute B, C and D to give rise to two more terms, add them all together, you're going to get 0. This is a familiar restriction on structure constants, which we have already met before. The new restriction that we get involves these new constants with two indices, CABC, CAD. Here, of course, B, C and D are the only free indices. A is a dummy index of summation. When cyclically permuted among B, C and D and added together, would give you 0. Now, there's one reason why I've written these two equations just beneath each other. Can immediately see from the structure that if the new constant CAB were related to the structure constants by the following rule, CEAB times phi E, where phi E are just real numbers, then the second relationship, the one in blue, will automatically be satisfied given that the first one is. These real numbers phi's are very easy to interpret. If you think of shifting your generators TAs to new generators T tilde A's, which are just the original TAs plus phi A times the identity, then the commutator between T tilde B and T tilde C will turn out to be the commutator between TB plus phi B and TC plus phi C. Of course, phi B's and phi C's commute is everything. So this is nothing but just the commutator between TB and TC. And that, of course, is ICABCTA plus ICBC identity. But now, if CBC is actually CABC times phi A, all you have to do is rewrite this as ICABC times TA plus phi A, and that is ICABC T tilde A. In other words, the central charges in the Lie algebra that we had before, these additional pieces which commuted with everything, can be simply gotten rid of in this manner. all you have to do is redefine your generators by adding the constants phi a to them. This, of course, would be valid only if CAB, these constants, were equal to CEAB times phi e. Notice that this is definitely a possibility given the condition which our constant satisfy. However, this is not necessarily the only such possibility. There could, of course, be other two index constants which would not be possible to write down in terms of the structure constants in this manner. Now, whether a given Lie algebra allows non-trivial solutions for CAB depends on the algebraic structure of that particular Lie algebra. Now, if all solutions for CAB are of the trivial nature, then we are a long way towards establishing that all representations of this particular Lie group has to essentially be non-projective. Even if we have projective representations, the phase factor can simply be gotten rid of by redefining phases of operators. In other words, all such phase factors will be in the trivial Tuco cycle. However, this is not the complete answer. The complete answer to this question is essentially given by this key theorem that we are going to enunciate now. No representation of a given group is intrinsically projective. And that means, of course, that even if it is projective, you can get rid of the phase factor by redefining phases of the operators involved, if the following two conditions hold. The first condition is the one which I have stated right now, that the generators can all be redefined by just shifting through by a constant to eliminate all central charges. This, as we have just seen, happens if the only possible solutions for CABs are the so-called trivial ones. But this is actually not all. This is the purely algebraic aspect of it. But algebra alone will not be able to guarantee that you do not have projective representations or intrinsically projective representations. The other very important condition that this theorem states is the following. The parameter space of the group must be simply connected. In other words, if you take the manifold of all the values for the parameters which describe group elements, any loop in this particular parameter space can be shrunk continuously to a point without ever leaving that parameter space. So this is a purely topological issue, and it deals with the question of what the fundamental group or the first homotopy group of the corresponding parameter space is. Now, instead of saying the parameter space of the group is simply connected, we usually say the group is simply connected. Now, it so happens that some of our very important and familiar groups have parameter spaces which are not simply connected. In fact, the group of rotations and, by extension, Lorentz transformations happen to be such an example. There are certain interesting things that can happen to representations because of this particular feature. And we are going to explore that in the other parts of this section. In the next section, what we are going to do is give a proof of this particular key theorem. This actually is in an appendix to the second chapter in Weinberg's book. It involves a bit of non-trivial mathematics, but delving into this would also clarify for us ideas about Lie groups and their composition rules, as well as some amount of algebraic topology, at least the part we need. I understand that not all of you who are listening to these are experts in either Lie group theory or differential geometry or algebraic topology. In fact, neither am I. But I'm sure that I will be able to explain the ideas involved so that you don't have too much difficulty in following along. But that is for the next lecture. Bye for now.